So in the previous few steps, I was able to determine that the voltage from C to D provided by the circuit, so the voltage that Zener diode would see is a reverse bias, so minus 9.633 volts, which is just barely over the Zener diode rating of 9 volts that we saw in the previous around the given schematic. Okay, so since that diode has greater than 9 volts in the reverse bias condition, okay, so it does see greater than 9 volts, if we were to build and measure this thing, we would see that the diode would start allowing more and more current in order to make that C to D voltage, that reverse bias voltage, be the 9 volts. And the negative just indicates that if I was measuring point from C to D, red lead on C, black lead on D, my meter would show a negative 9 volts. So polarity from C to D is minus to plus. Okay, so all that being said, basically what I do know is that since I have greater than 9 volts, the diode will hold that voltage to be 9 volts as long as it doesn't exceed the specs and explode or burn up. Okay, so as long as we're within some kind of reasonable spec, that diode will try as hard as it can to make it be 9 volts. Alright, so let's go in and now that we know that, all of these initial voltages that we found that the diode would have saw at the time of power up, those voltages are now going to change by just a little bit because we're just barely over that 9 volts. But essentially all these voltages are now different. So we're going to resolve, now that we know this voltage and polarity, C to D, we'll resolve all those outside resistors, and then we'll know the final voltages and currents for those outside resistors, which will allow us to, basically we still need the A to B voltage to figure out where that capacitor will charge. So let's go ahead and just get that finished up right now. Alright, so I've rewritten my circuit here. I'm going to come in here, and since I know BCD has been found, and it will be minus 9 volts. Okay, that's our final VCD voltage. Alright, so that means the current will be flowing, electron flow, from C to D. So when we find that number, that'll be minus or opposite of initially what we may have thought. Okay, alright, so I know that voltage. Now I need to solve my outer loops and my so what I'll do here now, let's just show that. So I'm going to solve this loop over here where basically from the supply V1 all the way to C to D and through the diode and back through R5 and R6. So the R1, R2, R5, R6 loop. And I'm also going to solve my C to D, my diode voltage, R3, V2, and R4. Okay, so my plan is I'm just going to do those two loops and determine the currents, the final currents in those resistors, and then from there determine the voltage drops. And then we'll do some double checking. Alright, so let's just start with the smaller of the two loops. Okay, so let's just designate some waypoints here. So I'm just going to call this loop A, and then this will be loop B. Alright, now I know this voltage and polarity here, so I'm going to write that in. Alright, so I've established the polarity, so I'll just write 9 volts right here. So I wouldn't write minus 9 volts because putting the polarity on the component takes care of that for me. And since I have that polarity, okay, I'll just go ahead and keep the polarity for that V2, and nothing should have changed for the polarities on those resistors. Those are all series aiding. The power supplies will just keep those polarities the same, and they aren't fighting each other. So I'll go ahead and write those polarities in as well, plus to minus. Okay, so now my loop B, the smaller of the two loops, I've got all my polarities written in. So I'm going to go ahead and do my loop equation. So I'm going to start here just out of my personal habit. I start in the bottom left corner, not any real reason, just I like to do things the same so that I don't have to try to think too hard. Okay, so I'm just going to go in a clockwise manner, and as I encounter polarities, I will use them, and as I can encounter known voltages, I'll use those. Those resistors, I will just I'll have to solve for what those values are. So that's kind of the plan. Let's just go for it. So 0 equals, always 0 equals, and I'm coming up and I see plus 9 volts. Okay, so I've gotten through D1, and then I'm coming around to R3 plus VR3, coming around minus 16 volts. It's a known voltage and polarity. And then back to R4 plus VR4. All right. Okay, well, that's okay, I guess. All right, so now it's just a matter of doing a little bit of simplification and reorganizing my terms. So 16 volts on this side minus 9 volts equals VR3 plus VR4. Alright, so 16 minus 9, that should be 7. Okay, let's hope that let's see how my mental math is doing this morning, because it's the easy things that have turned out to be hard. Whoops, no, I kind of did that right. 16 minus 9, there we go, 7 volts. Okay, so 7 volts. So 7 volts. So the sum of VR3 plus VR4, whatever they are, will be 7 volts. Okay, well, let's see if we can solve this thing a little bit, or reorganize, expand some terms. I'm going to use my knowledge of Ohm's law to expand my terms. I'm going to call that current in that loop my loop B current, or my IB. Alright, so I've got IB times R3 plus IB times R4. Now I can just factor 7 volts equals IB in common with both terms, and it's just R3 plus R4. Okay, so now I can actually solve this thing. 7 volts over the sum of R3 plus R4 equals that B current, that loop B current. IB equals, let's bring that calculator back and solve it. So 7 divided by, and 110 plus 150. I got everything in the right spot. Alright, 26.92. 26.92. Alright, so that seems right. Let's just verify. So minus, or plus 9 volts plus VR3 minus 16 plus VR4, okay, all equal to 0. Alright, so far so good. as long as I've put all my terms in the right spot and gotten my polarities set up properly, that should be my loop B current. Alright, which is great. Okay, let's do some verification here. And okay, so I'm just going to fill in and plus minus, okay, and minus, whoops, yeah, minus plus, okay, so all my supplies are in agreement, and so my polarities are series 8ing all the way around the outside on those resistors, so those should be pretty readily apparent. Again, I'm going to ignore this capacitor for the moment, and I'm going to write a loop equation now for my A loop. Okay, let's just start over here, and as always 0 equals, and I'm encountering, let's get that polarity just to be clear about it, minus 20 known voltage and polarity, plus VR1, okay, plus VR2. Okay, now I'm going to head down through that diode, and it is a known voltage and polarity. As I come down, I'm hitting that minus side. It's a known minus 9 volts. Okay, hitting R5 plus VR5 and plus VR6. Alright, now I'm back to where I started. Alright, so now this loop is going to be 20 volts plus 9 volts equals the sum of VR1 plus VR2 plus VR5 plus VR6. Alright, well that's cool. So this hopefully is pretty easy math. 29 volts equals, now I'm going to go ahead and write this out and factor it at the same time. So I'm expanding each of my terms to IA times each resistor. So each resistor, or basically those voltages, will have IA in common. And so I'm going to go ahead and just do the factoring and writing at the same time. If that doesn't make sense to you, then see the previous step where I did that for loop B. So IA times the sum of R1 plus R2 plus R5 plus R6. Alright, so now 29 volts over R1 plus R2 plus R5 plus R6. It's going to be IA. So IA equals, let's get that in there, see if we can get that into the calculator properly. Clear that out. So 20 plus 9 better be 29. Okay, so 29 divided by, well, let's make sure we get these in there. R1 is 110 plus 130 plus R5 is 220 plus R6 is 750. That's what I've got written down there. Okay, so 23.97 milliamps. 23.97 milliamps. Alright, so this should be the final currents in my final circuit. So we determined earlier we're going to treat that capacitor as if it has a full charge, so no current is flowing that direction. And we determined that D1 will be reverse biased, and that Zener rating voltage will be present.